All right, welcome to this session. Are you able to get me clearly? Hello?
Yes, we can hear.
Okay. So let's look at atomic structure, specifically on quantum numbers. So we are going to actually, as always, this is a revision class, meaning we are just going to be centered on the basics of what quantum numbers are and how we can handle questions on quantum numbers. Okay. So now, to start with, quantum numbers, these set of values, okay? So these are set of values used to describe the electron state in an atom. So we are saying these are basically these are set of values which are used to describe the electron state in an atom. There are 4 types of quantum numbers that we are going to look at. So we basically have 4 types of quantum numbers. The first one is principal quantum number. Principal quantum number. So this principal quantum number is denoted by small letter n. Okay. So what does principal quantum number do? So this quantum number represents the energy level of the electron. Okay. So it represents the energy level or shell. Sometimes I think we are familiar with shells. So it represents the energy level or shells of the electron. So principal quantum number will just give us the information about the energy level, where the electron is. Is it in energy level of 1? Is it in energy level of 2? Is it in energy level 5? That's what principal quantum number is. So values for principal quantum numbers start from 1. So values for n will not start from 0 because we cannot have energy level of 0, but instead they start from 1. So we can have energy level of 1, energy level of 2, energy level of 3, energy level of 4, etc. and etc. So you can view principal quantum numbers as those shells that you used to like draw. Okay, let me give you a hint. Back then we used to draw something like this. I'm not saying this is how it is, but observe what is happening. So we can call this as energy levels. Like here, this can be observed to be 1, energy level of 1. This can be 2, going just like that. So observe what is happening. The larger the n, this structure here is becoming what? Large as well. Meaning that the electron which is residing in the last shell will always be away from the nucleus. if this is the nucleus here. So the larger the n, the more time the electron spends far from the nucleus. Okay, so that's basically about the principal quantum number. So you can have energy level of 2, energy level of 3, energy level of 4, just like that. And then the second one, the second type is angular momentum. Angular momentum, quantum number. So angular momentum quantum number is actually represented by small letter L. Okay, that's angular momentum. So we use small letter L to represent angular momentum. So that's the second quantum number. Remember, the first one is the principal, so the second one is angular momentum. What does it do? So this one determines the shape of an electron. Okay, so this one, it determines the shape of the orbital. That's what angular momentum do. So now, the values for angular momentum, remember for principal quantum numbers, we said values start from 1 going up, 1, 2, 3, etc., etc. Now, for angular momentum, L values starts from n to n minus 0. So the values for L starts from 0 to n minus 1. So the idea we are trying to put across is that it is dependent on the value of n. So what do we mean when we say the value starts from 0 to n minus 1? For example, if given that n is equal to let's say just 2, what is L? Okay, what is L? Meaning, what is the angular momentum for this part? So basically, this is the principal quantum number. We are told that the principal quantum number is 2. And what is L? So L is equal to 0 to n minus 1, meaning the values, it is 0 to where? 2 minus 1. And what is 2 minus 1? Because we know n is 2, so it is 0 to 1. Okay? Meaning that the values of L is equal to 0, comma what? 1. This is what it means, 0 to n minus 1. So if we had, let's say, n is equal to 3, which means our n minus 1 was going to be 2. So the values of L was going to be 0, 1, 2, 3, because the last value must be n minus 1. So again, if we have n.
Sorry, Mr. Kunda, could you repeat the last part?
Okay, so we are here. If we have the value, we are looking for n, right? I mean for L, given that the principal quantum number is 2. Okay, let me use another example. For example, if the principal quantum number is 3, then what is L? Okay, we want to find the angular momentum for n is equal to 3. So the whole principle is that L, to get the values of L, you should understand that L ranges from 0 all the way to n minus 1. So this is the way you get the values of L. So now, what do we have as L? I mean as n? Our n in this case is 3. So where there is n, we put 3. So meaning our values must range from 0 all the way to n is 3 minus 1. So our values must range from 0 to 2. What are those values? So now, to give the exact values, you say L is equal to 0, 1, all the way to 2, because that's the range where we need to stop. Because L is from 0 all the way to n minus 1. Is that okay now? Hello? Have you gotten the point?
Yes, it's fine.
Okay, perfect.
Yeah, it's fine.
All right. So that's how you basically get the value of L. So meaning angular momentum is dependent on the value of n. You have a lot of values of L as long as the n is also what? Large. So for example, if n is equal to 4, meaning that your angular momentum will range from 0 to 3 because the last value must be n minus 1. Right, so let's go to the next board and look at the third quantum number. So the third quantum number is given to be magnetic quantum number. Magnetic quantum number. So magnetic quantum number is given by small letter m, L. So ML indicates the magnetic quantum number. So what does this quantum number do? So magnetic quantum number would actually determines the orientation of electron in the orbit. So this determines the orientation of the orbital in space. Okay. So now, after understanding that, how are the values actually ranges? So now, on the orientation part of the orbital, if you want, you can say it determines the orientation of the electrons orbital in the subshell. So now, we have got values for magnetic quantum number. So these values actually ranges from -1 all the way to positive n. Oh, okay. So values for ML how do they appear? So they appear to be in the form of -L. So this is L, -L, to positive L. That is how you get the magnetic values, magnetic quantum numbers value. So it's negative L to positive L. So the idea is that you'll be dealing as if you're dealing with you'll be dealing with values that are ranging. Now you'll be given the range from negative side all the way to the positive side. So for example, what do you mean when you say the quantum numbers ranges from negative L all the way to positive L? First thing first, you need to understand the fact that for you to get L, you should have N. And how do you deal with N? So basically, for example, if N is equal to 2, okay? Find ml of this. Right. So first of all, what we have is N is equal to 2. What is L? We know L is from 0 all the way to N minus 1. So this is equal to 0, what? 1. So that's L value we have. So we have two values of L. So we have L is equal to 0, and we also have L is equal to 1. Now the goal is to find, for each L, you should find the value of ml. So when L is equal to 0, what is ml? ml is basically negative 0 to positive 0. It is simply 0 because 0 has nothing. So ml, when L is equal to 0, ml is what? 0. And when L is equal to 1, ml is equal to what? Negative L to positive L. So meaning it is from negative 1, 0 all the way to positive L, which is in this case, our positive L is 1. So all the way to positive 1. So meaning that when L is equal to 1, ml is equal to what? 3. When L is equal to 0, ml is equal to what? 1, or basically just 0. Is there a question?
Sorry, Mr. Kunda. So like since you mentioned that the ml, like we've written down their values. So when they ask you for the ml, you just count how many they are, or first you list and then you state how many they are.
Well, in case they ask you for the total number of ml, then that's when you count. Meaning that if for n is equal to 2, when n is equal to 2, total ml, meaning total orbitals, you now count, which means this is an orbital 1, 2, 3, 4. So now you add the total when they ask you. But in many cases, when they just want you to show the ml, you just have to list in this form. But in a case where they want you to give the total ml, I mean the total number of orbitals, that's when now you count, because these are the same we are referring to as orbitals now. You understand now?
Yes.
Okay.
Yeah.
So now let's look at something like a table that will actually help us to like understand some ideas on ml and everything. Let me put everything on one table. So let's
I
say,
have a question.
yes, please.
When n is equal to 2, is this supposed to be just 1? Why didn't you include the 0?
Because the total values of ml when n is equal to 2. What's the total values of ml?
I'm talking about the L.
Why did I include the 0? Because ML ranges from 0 all the way to n minus 1.
All right, thank you.
Okay. Okay, let's look at this. What will happen? What will be the total number of orbitals when n is equal to 4? Let's look at this example. What is
Why do you keep on switching on and off? You were about to say just now.
what is the total number? What is the total number of orbitals associated? What is the total number of orbitals associated with the quantum number n is equal to 4? Now we have such a question. So if you have such a question, okay, what do we do? First thing first, we should find, for us to get the total number of orbitals, meaning they are looking for the total number of ML values. That's the whole point there. How do we get to ML? First, we need to deal with L. We need to find the values of L. So we are here. So when n is equal to 4, okay, L values now will be equal to what? 0 to n minus 1. So the L values will be equal to 0, 1, 2, and 3. Because the range for L is 0 all the way to n minus 1. Meaning that we have 0 all the way to 4 minus 1, which is equal to 3. So 0 all the way to 3. Then you give this range. So that range is this one we have here. Meaning that we have L is equal to 0, L is equal to 1. So these are separate values of L. So we have L is equal to 0, L is equal to 1, L is equal to 2, and L is equal to what? 3. So remember that for each L, we should be able to get ML. Okay? For each L, you have to get ML. So when we are on L is equal to 0, ML is also equal to 0. Remember, ML, we get it by saying ML is equal to negative L all the way to positive L. So when we are here, ML, when you're dealing with 0, 0, nothing is changing. So it's like a number line. So now when L is equal to 1, ML is equal to negative 1, comma, 0, comma, positive 1. Okay? When L, my board, okay, let me write it here. When L is equal to 2, now, so we are answering when L is equal to 2. When L is equal to 2, ML is equal to negative 2, negative 1, 0, positive 1, positive 2. Okay? And when L is equal to 3, ML now is equal to negative, negative 3, negative 2, negative 1, 0, 1, 2, 3, in that order. So these are the ML values we have for this point here. Now, how do we get total orbital? So we basically have to count all the MLs, we add them together. That will give us the total number of orbitals. So when ML is equal to when L is equal to 0, ML is equal to 0. So we start counting. So for this one, the total ML values is 1, 2, 3, 4, 5, 6, 7. So here it's 7. And here it is what? 1, 2, 3, 4, 5. So when L is equal to 2, ML is equal to 5 total. And when L is equal to 1, ML is equal to 3 as total. And when L is equal to that, ML is 1. So now we add. Therefore, total orbitals total orbitals is equal to 1 plus 3 plus 5 plus 7. So this will give us what?
16.
It will give us 16, meaning when N is equal to 4, the total number of orbitals is 16. So that's how you get your values. So observe that all these orbitals have the same energy level, no matter how different they are. Of course, they are in different magnetic quantum number. Hello, are you able to get me? Hello? I was kicked out of the classroom. So basically what I was saying is that because you guys have the energy levels there, observe that even if we have the total number of orbitals, so total number of orbitals, we found it to be 16, okay? Even if those are in different magnetic quantum number, okay? Even if they are in different, just the orientation, okay? It's a bit of a complex thing to explain, but just the orientation. Now, what that means that they are all still coming from the parent energy level of what? 4. So this is the main energy level. or we can call this as the parent energy level. Meaning that though there are a lot of orbitals, yes, Cecilia.
Sorry, sir, your network is breaking, so we can't really hear you.
You can't hear me.
Sir, we can't hear you.
Okay, let's end the meeting. This one, and log in the next one. Just now, the same link.